We now turn our attention towards the Claisen condensation, which is the addition of an enolate to an ester instead of to an aldehyde or a ketone. So here's an example of the classic Claisen condensation, which is the self-condensation of an ester. So in this reaction, 2 molecules of ethyl acetate, the quintessential ester, are treated first with sodium ethoxide as a base. We'll talk about why that's important in a few minutes. Followed by an acidic aqueous workup. We're also going to talk about why that's important to this reaction. And then the product here is called ethyl acetoacetate, and it is an example of a beta keto ester. That, of course, means that 2 carbons away from the ester carbonyl is a ketone carbonyl. Another name for such beasts is a 1,3-dicarbonyl compound. And then the byproduct of this reaction is a molecule of ethanol. So let's dive right in and consider the mechanism of this reaction. So in the first step, just like in the case of the aldol condensation, we deprotonate the alpha hydrogen. In this case, it's alpha to the ester carbonyl group instead of alpha to an aldehyde or a ketone carbonyl. But we deprotonate the alpha hydrogen in order to form an enolate. Then in the second step, that enolate is added to another molecule of neutral ester. Okay, so ethoxide is pretty similar in base strength to hydroxide, so you're also going to get only a small percentage of the ester being converted to enolate, and there's going to be a lot of ester around for the enolate to react with. Okay, so you have your nucleophilic addition step, and that yields us with the tetrahedral intermediate that you can remember from the acyl transfer mechanism. Okay, so it's just like all of the acyl transfer reactions we looked at with esters, but in this case, the nucleophile is an enolate instead of an alkoxide or hydroxide or something similar to that. Okay, so we have our tetrahedral intermediate, and then step 3 is expulsion of the leaving group to regenerate the carbonyl compound, and it looks like we're done, right? We've done our 3 steps of a base catalyzed acyl transfer mechanism. Of course, it's not an acyl transfer mechanism, it's a Claisen condensation, but you get these similarities. But then I have 2 more steps here drawn in my mechanism. Step 4 then is deprotonation of the extremely acidic hydrogen alpha to 2 carbonyls. That central hydrogen gets deprotonated under the reaction conditions, and I'll have more to say about that on the next slide also. So if that central carbon has been deprotonated, we now have a molecule with an overall negative charge. We want a molecule that is neutral overall. So as a result, the final step has to be an acidic workup where we add acid and water in order to give us the neutral compound we desire at the end of the reaction. Okay, so a few notes. I said I would talk about some of these things, details, in a few minutes, and now it's time to talk about them. So first of all, you notice I used sodium ethoxide as the base in this reaction, and I have never used sodium ethoxide as a base in a reaction before. So there must be some good reason why I used sodium ethoxide instead of sodium hydroxide. And the answer is that if you were to use sodium hydroxide as a base, you have already learned a reaction of esters with sodium hydroxide. It is called hydrolysis. It is a rapid and irreversible reaction, and that's going to, of course, take precedence over the Claisen condensation. Now, the next question is, even if we are using ethoxide as a base, you have also seen reactions of esters with alkoxides. They are called transesterification reactions. So can't the base add to the ester and carry out a transesterification reaction? The answer is yes, absolutely. That can happen, and that does happen. Therefore, you want to be sure that the alkoxide base that you use has the same R group on it as the ester. So in this case, we're starting with an ethyl ester, so we want to make sure that we use ethoxide as the base. Okay, now on to this issue of the acidic hydrogen. So as I said on the previous slide, we have the final product after step 3, but the reaction is not done. It keeps going whether or not we want it to. Okay, so recall that the hydrogens on carbons next to 2 carbonyl groups are much, much more acidic than the hydrogens alpha to 1 carbonyl. Okay, so they have a pKa in the 9 to 10 range for the hydrogens between 2 carbonyls, as opposed to a pKa of 19 for an alpha hydrogen of a typical carbonyl compound. And this, of course, is due to the stabilization imparted by an additional resonance structure. Okay, so this carbanion can have a resonance structure where its negative charge is on the right-hand oxygen or its negative charge is on the left-hand oxygen. And also drawn here is the resonance hybrid. That negative charge is now shared by 3 atoms, 2 of which are electronegative oxygens, instead of just shared by 2 atoms as in a normal enolate. So as a result, because the pKa is so low, 1,3-dicarbonyls are acidic enough that hydroxide or alkoxides can deprotonate them irreversibly, which is step 4 of this reaction. Irreversibly, this is not an equilibrium step, single arrow, and we can't stop this from happening. That's why we need the extra acidic workup step in order to get the neutral product. Okay, so having talked about those features of individual steps, I want to finish this discussion by talking about equilibrium considerations for the reaction overall. So through the first 3 steps, delta G is going to be positive for this reaction, which means if that was all there was to it, this reaction would not take place. We would not be talking about a Claisen condensation, and Ludwig Claisen, who discovered it, would not be a famous chemist. Well, recall that delta G is equal to delta H minus T delta S. So if we want to understand this, we've got to look at what the delta H term should be and what the delta S term should be for the reaction up till this point. Well, delta H is going to be positive because esters are more thermodynamically stable than ketones are. Okay, we've seen plenty of examples, such as reactions with sodium borohydride, where ketones are reactive and esters not. This reaction replaces an ester with a ketone fundamentally. You start with 2 esters and you're ending with a beta keto ester. So therefore, that's going to be uphill energetically. Delta S is going to be negative because 2 molecules are coming together to become 1. That is entropically unfavorable. So both the delta H term and the delta S term are working against us for this reaction. However, in step 4, the fact that step 4 is favorable, very favorable, and irreversible, that drives the equilibrium towards products. So this proton transfer, this deprotonation step, is not just an undesired nuisance. It is essential for driving the equilibrium. And one more note about this, now that we have established that the Claisen condensation is only a useful reaction if you can do this deprotonation at the end, in order for this deprotonation step to take place, the starting ester must have at least 2 alpha hydrogens. Okay, ethyl acetate that we looked at is no problem. It has 3 alpha hydrogens. So one of those alpha hydrogens gets removed in the initial enolization, and then the second one has to be removed at least temporarily in step 4, which we now know is required. That hydrogen is going to get put back on in the end, but we have to have that step in which we remove that alpha hydrogen. Okay, so that's the introduction to the Claisen condensation, and in the next couple of lessons, we'll look at some of the variations on the Claisen condensation, just like we looked at some of the variations on the aldol condensation.